So the next question is what actually is the current density, which is J. J equal question mark. So let's define what is exactly the current density. The formula speaks for himself. It's the current equal to integral of J, which is a vector, dot dA. dA is the familiar area differential vector. So what's the meaning of J? You can see it from many directions. One of them is the units. You see this is ampere, this is meter square. We know that A is meter square. Integral don't have units, it's just summation. And J must be ampere per meter square. And the concept of J is saying that if I have this coin in front of me, some resistor, and I come in with all the mighty current through this coin, I want to ask you, is the current over this point equal to the current over this point equal to the current over this point? Nobody said it should be the same. Maybe it is, maybe it's not. So we define this tiny area, which is dA, and J multiplied by dA is the specific current that goes through this small differential area. So another way to think about that, let's give another analogy, example from other place that maybe you are familiar with, is talking about force and pressure. So force, we know that the formula for force is actually integral of the pressure dot dA. The same concept. Okay, for example, if I want to do a handstand, okay, I want to take my two hands and press the floor and stand only on my hands. Who said that the force that I feel in this point equal to this point equal to the pinky? Okay, each place have different force applied to him. So if you're gonna draw my hand, this is my hand, right? So what I'm gonna do, I'm gonna divide the area of my hand to sub areas. Here you can see each one of them is actually dA, and each one of them have some small force applied on it. For example, if I'm tilting a little bit to the front, I would push with my fingers more at my handstand to balance me. And if I'm falling to the other way, I'm gonna do it with the wrist, right? So I'm gonna play with the force that I have. So each square have dF. And what is this dF? Is the pressure, which is this Newton over meter square, multiplied by dA, which is meter square. So this is the analogy that I want you to keep in mind from other classes. Okay? Vector and vector. This is the analogy. It's the same thing with the current. So the current, nobody said it would go from the same amount for each side. Okay? So in our case, okay, J is constant. Just in our case, I want to emphasize that in the future we're gonna see many current density, different current density. But in this particular point, we said that the coin is uniform. There's no difference in the material over here, in the material here, in the length of the coin. Everything is the same. So there's no reason for the current to say, I prefer to go that way. It's better for me. No, it's not happening. So we can say that J in our case, let's do it in red, it's just our case, is some constant. The direction of J and dA are in the same direction. I can get rid of the vectors. J can go outside of the integral because it's constant. And then I have integral over the area, which is the area of the coin, which is pi a square. So I know that I equal J multiplied by pi a square. So the result is that J actually equal to I divided by the area. I divided by the area, which in our case it's a circle, so it's pi a square. And this is the same for every coin, because when I go through one coin, now what I'm facing, another coin. I'm gonna do the same thing, so J gonna stay constant for each resistor, for each coin. So that's something was really important to mention. So that's how we find GA. The next question gonna be about energy. So let's talk about energy. So when they measure the height of the structure of the coins, the pillar of coins, then they saw something, they see something, actually feel something crazy. When they try to, to take off the coins and tear this apart, they feel that the coins are hot. Do you ever notice when you talk to the phone, sometimes it's getting really hot? Why so? Okay, so let's talk about that. The question here is, what is the power of the coin tower? Okay, this is the question. What is the power? And what is power? Power is, think about that energy is like money. Bill Gates get $17. What's $17? It doesn't mean anything. $17 per second. That's the reason he's the most rich guy. No, it's I think the manager of Amazon right now is the most rich man in the world. But in our case, the idea is that you can't talk about money without talking about time. We want to know the ratio. Okay, so you got that amount of money in which time? The same thing in electricity. When you talked about energy, it's not that interesting. You want to talk about energy per time. And this idea is called power. Okay? So what is power? P is actually equal to energy, which we are defining as U, dt. The derivative of the energy. If I want to talk about the speed is how much displacement I have in my location, right? In x. So I divide the x by the place. And if I want to know what the change in energy by time, I'm gonna derive by time. So we already know what is actually U. U is actually, we know that we can speak about electrical potential as VQ, right? In our case, the battery is constant. So I can take V0 outside. So V0 multiplied by dQ led to dt, right? And what is this? This is maybe familiar to you from the lecture that you had. dQ to dt is actually the definition for the current, I. So the power of a resistor is actually V multiplied by I, okay? So another stupid way to remember stuff, you know that somebody give you V when you do it right, so if you have power, good for you, get a V. That's how I remember it, stupid way. We can also, make it even more simplified by using Ohm's law, the Veer law, right? And put, instead of V, I. And then I see I square R. Another interesting way to present what is the power. How much energy do they do in time? The units are watts, okay? And watts is actually joule per second. Okay, so this is the same idea, the same concept. So if I want to know what is actually the power that I'm using, I just gonna substitute I, square it, and R, which we already found. So it's easy, or maybe V0 and I0, and that will tell me how much energy being consumed by this pillar. So you know that when they touch the pillar, they feel that this is hot. Why? Because every second, boom, 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 it's produced that amount of joule. You have the experience when you touch something, hold it, and then say, it's really hot. Why so? Because when you hold it, it was not enough energy to actually hurt you. But after a few seconds, it was generating enough energy. You gave that a delta of time. There was enough joule to make you feel the pain. So this is the concept behind that. We finished the first question. Let's move on to the next question.